Dear students, now we are going to discuss about logic gates and its types in detail.
Logic gates are digital circuits. These all are used as the building blocks of any digital system. Simply, we can say it is an electronic circuit having one or more inputs and only one output. In general, logic gates are having one or more inputs, but there is only one output. We are going to use zeros and ones, that is binary values in logic circuits. We can categorize the logic circuits into three types: basic type, universal type, and special type. In basic type, the gates are AND gate, OR gate, and NOT gate. Universal gates are NAND gate and NOR gate. Special gates are XOR gate and XNOR gate. So let's discuss each gate in detail. An AND gate has two or more inputs and only one output. AND gate represents the multiplication operation, so the output is equal to the product of all inputs. This is the symbol of AND gate. Here we are using two inputs A and B. The output Y is equal to A dot B. The operation can be represented by using the truth table. So it is the table where we can relate the output with the inputs. Here inputs are A and B. Output Y is equal to A dot B. 0, 0. The answer is 0. 0 into 1. The answer is 0. 1 into 0, 0. 1 into 1 is equal to 1. So from this truth table, we can simply explain the operation like this. If one of the inputs is low, see here, if one of the inputs is low, then the output is also low. When both the inputs are high, then only we can get the high as the output. So here when both the inputs are high, the output is also high. Nowadays, the AND gates are available in terms of linear integrated circuits, that is IC. So here AND gate ICs are represented like this: IC 7408. This 7408 IC has 4 numbers of AND gates in it. OR gate has 2 or more inputs and only one output. OR gate represents the addition operation. So the output is equal to the sum of all inputs. This is the symbol of OR gate. Here we consider two inputs A and B. The output Y is equal to A plus B. The truth table for this OR gate is given like this. Inputs A and B. Here output Y is equal to A plus B. 0, 0. That is 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1. So from this truth table, the operation can be explained like this. If one of the inputs is high, then the output is also high. Here we can see one of the inputs is high means the output is also high. When both the inputs are low, the output is also low. Here the OR gates are also available in chips. Okay, IC. Here the IC number is 7432. NOT gate, that is also called as inverter. It is a single input and single output gate. Output is the complement of the input logic. Complement means it is an inverting output. That means the truth table is given here. Input is A, output is A bar. Here bar represents the complement of the given signal. If input is 0, the output is 1. If input is 1, the output is 0. It is a single input and single output gate. The symbol for this NOT gate is like this. Okay, there is a bubble. Bubble represents the inverting operation. If A is the input means I can get the output as A bar. The NOT gate IC is IC7404. In this IC we are having 6 NOT gates. So this is the final comparison of basic gates: OR gate, AND gate, NOT gate. OR represents what? Addition operation, that is sum of the inputs. AND represents the multiplication operation. Here it is the product of the inputs. NOT gate represents the complement of the input. So here these all are the symbols used. And y is equal to here a plus b. For AND gate, a dot b. For NOT gate, y is equal to a bar and its respective truth table. Universal gate is a gate which can be used to implement any other gates without using other types of gates. So the single gate is used to implement any other gates. There are two universal gates. First one is NOR gate, next one is NAND gate. Let's discuss each one. NOR gate. NOR gate is also called as the combination of NOT and OR. It has two or more inputs but only one output. Here the output is the complement of the sum of the inputs. Okay, the output is the complement of the sum of the inputs. R represents the sum operation. For that sum we are going to take the complement. Okay, so here the symbol can be represented like this. NOR gate symbol is the general form of OR gate along with this bubble. This bubble represents what? NOT gate. Correct. So this is the OR plus NOT. This OR plus NOT can be combined together as the NOR gate. Here A and B are the inputs. The output of the OR gate is A plus B. The NOT gate gives the complement of this OR gate. That is called NOR gate. Okay. So truth table for this NOR gate is, here inputs are A and B. A plus B is the output of the OR gate. Okay, so 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1. This is for the OR gate. Here NOR is nothing but the complement of OR. Correct, it is the complement of OR gate. So we can simply take the complement. 0 becomes 1, 1 becomes 0, 1 becomes 0, 1 becomes 0. So from this truth table, we can understand when both the inputs are low, then only we can obtain high output. If any of the inputs is high, the output is 0. Okay. So next one is NAND gate. NAND gate is the combination of NOT and AND. That means it is the complement of the NAND operation. It has two or more inputs but there is only one output. That output is the complement of the product of the inputs. Okay. So here this is the symbol of NAND gate. So NAND gate is the combination of AND gate and NOT gate. Correct. So here two inputs A and B. This is the representation of AND gate. The output is A dot B. That is given to this NOT gate. then the output becomes the complement of the AND gate. The complement of the AND gate is nothing but NAND gate. So these two is combined together to produce NAND gate. So here this bubble represents the complement of this AND gate. Okay. So the truth table for this NAND gate is given here. Inputs A and B. AND operation represents the product, that is multiplication. NAND represents the complement of this AND gate. So 0 into 0 is equal to 0, 0 into 1 is equal to 0, 1 into 0 is equal to 0, 1 into 1 is equal to 1. This is for the AND gate. For this NAND gate, we have to take the complement of this. So this 0 becomes 1, 0 becomes 1, this 0 becomes 1, 1 becomes 0. So from this truth table, we can explain the concept like this. If any of the inputs is low, then the output is high. Here any of the input is low. Wherever 0 comes, then the output becomes high. If all the inputs are high, then only the output is low. When all the inputs are high, 1 and 1, for that alone we got 0 output. Okay. So next one is special gates. Special represents these are the exclusive gates used in a particular digital circuits. Okay. So the special gates are XOR gate and XNOR gate. XOR gate, that is called as exclusive OR gate. It is also represented as XOR. Okay. It has two or more inputs and only one output. XOR operation can be represented like the symbol plus with a circle. So Y is equal to A XOR. This is called as XOR with B. A XOR with B. So that is given like this: A B bar plus A bar B. So this is the explanation of this XOR operation. Here we are having two inputs A and B. This is the symbol of XOR gate. That is exclusive OR gate. So Y output is equal to A XOR with B. The truth table for this is given like this. So inputs are A and B. Output Y is equal to A XOR with B. This A XOR with B is nothing but what? A B bar plus A bar with B. So here 0 plus 0, that becomes 0. 0 XOR with 1, that is equal to 1. 1 XOR with 0 is equal to 1. 1 XOR with 1 is equal to 0. So based on this principle, okay, so A B bar plus A bar B, we can obtain the answer like this. So from this truth table, we come to know that if any one of the inputs is low, then the output is high. When both the inputs are same, that is both the inputs are low or high, then the output is low. So this type of XOR gate is widely used in half adder, full adder and subtractor circuits. Next one is XNOR gate, that is exclusive NOR gate. It is also represented as EX, that is XNOR gate. It has two or more inputs and only one output. That output is the complement of the XOR gate. So we have just now discussed here about XOR gate. We are going to take the complement of the XOR gate for this XNOR gate. So this is the symbol. Here this exclusive NOR gate is the combination of XOR and complement, that is NOT gate. Consider two inputs A and B. This is XOR gate. XOR gate produces A XOR. This is XOR symbol. A XOR with B. The complement of this XOR gate is nothing but A XOR B the whole bar. This is the output of the XNOR gate. So this XNOR gate is simply represented like this. The XOR gate along with this bubble. Okay, so this bubble represents the complement. So the operation of the XNOR gate is given like this. Y is equal to A XOR with B, the whole complement, the whole bar. That is equal to A into B plus A bar into B bar. The XNOR operation is simply represented as A XNOR with B. So the truth table for this operation is inputs A and B. Here XOR gate, that is A XOR with B. The complement of this XOR is nothing but XNOR gate. So here 0 XOR with 0 is 0. 0 XOR with 1 is 1. 1 XOR with 0 is 1. 1 XOR with 1 is 0. We know that the XNOR is the complement of this. So the 0 becomes 1. 1 becomes 0. 1 becomes 0. 0 becomes 1. So we can get these values by using this expression A into B plus A bar into B bar. So here whenever both the inputs are same, that is either low or high, we can obtain the high output. If any of the inputs is low, then the output is low.